Hi, thanks everyone for joining. I'm Martin Dietz. I'm from DuPont. Excited to be here and learn so much this week. I look back in time as how long I've been coming to TIDES. I saw a presentation that my colleagues and I gave in 2004. So excited to be here 19 years later, continuing to present on purification and things like this. So I really love talking about purification and this technology. So I put my email, my phone number. If you're ever bored, you want to text me, have a question, feel free to. I'm happy to talk about it. So DuPont has a number of bioprocessing resins. And DuPont's often known for a lot of technology for water purification or other technologies like that. But we do have a bioprocessing portfolio used for anything from plant to animal extracts, antibiotics, and vitamins and things like this. But a number of our products down here, especially in this AmberChrom range, are used in peptides and oligonucleotides. And so that's the focus of this talk today. Is really to focus on the XT chromatography line right down here at the end. I do thank the organizers because I see they used the inspiration of our resins as their backdrop here. And we do sell them in pre-packed columns as well. So I think by now we've heard this a lot about what the difference is and why we're talking about oligonucleotides here. We do have some other technology that we have a poster on where we're talking about nucleotide purification, really as a raw material into mRNA type of IVT applications. But for today, for this talk, we'll talk about oligonucleotides, which are in this 20 to 120, give or take, length. So they can be used for a lot of things. I mean, we're at a conference talking about cutting edge, and you hear about antisense and siRNA and CRISPR and guide RNA and things like this. But certainly it's used for other things in diagnostics, probes, primers. And at the end of the day, these are all typically manufactured a very similar way and purified a very similar way. So you can tell I'm a chemist here because there's a lot of hexagons and so forth. But this process of oligonucleotide synthesis, a couple things to take away from it is one, as you go around this cycle and you add bases, some things don't always work perfectly, and so you get some impurities. You get especially if you fail to couple a base here, then and you don't add to that hydroxyl group, what happens is out comes a capped material, and this ends up as a capped shortmer as an impurity that is often you'll see in the chromatography the N-1, 2, 3, 4, 5, whatever. They end up capped out as shortmers, and they don't make it all the way to the end, in which, when you cleave off of the support resin, end up as this DMT on material. So that's what we're going to talk about is purification of that DMT on material from everything else that's in there. So it's shortmers, there could be some other base deletion, branching, whatever sequences, and certainly deprotection byproducts in there, the amine solution, the solvents, and things like that. So people there's kind of two schools of thought on how to do this, or two preferences, is after the synthesis, if you want to get to the end of the day, a oligonucleotide that you can put in and use for your application, there's two steps. There's DMT removal and some type of purification. And so some people like to purify it first and then remove the DMT, or some people like to remove the DMT and then purify it to go into their next downstream steps. So what what we'll show today is about our reverse phase resins. You can take it through either one of these routes to get to that, that end product, which is your oligonucleotide. So the two resins that we'll focus on today are called AmberChrom XT resins. These are very small, spherical, very rigid particles that are made from a polymeric polymer. And these are used similarly, if you have this mindset, as a reverse phase chromatography. It's very hydrophobic surface. It's a pore structure surface, so it's high surface area, very hydrophobic polymer. And again, they come in pre-packed columns. You get them in little bottles, drums, pallets. You want us to back a truck up to your place, we can do that too. So let's start with this first route, is this DMT on purification. And there is a poster on this, and really what we'll talk here that is a bit new is we're really going to higher loading. When we first started going into this space, we were doing pretty low loadings, and some of our partners would come up to us and say, that's great, but we load at high levels of loading. And so that's what we'll focus on here, and then we'll talk more about the DMT off later. So if you think about the DMT on purification and why we really think this is a great idea, and some of our partners do as well. So if you think about that oligonucleotide coming out of synthesis, you have the backbone, your nucleotide, your oligonucleotide, and it's got this DMT group on at the end. So your oligo is anionic and has hydrophobic character, and that DMT really dominates the adsorption. No matter essentially how long this anionic group is, if it has a DMT on group, that drives the hydrophobicity, and it will adsorb to this hydrophobic polymer. And so here we show an example. You come out of synthesis, you have small molecules, you have all these failure sequences, you have your target oligonucleotide, and then you load it onto the column. And in this case, we loaded on a pretty hefty feed concentration, just a small injection of it to be able to see these peaks. And what you'll see comes right through is some of these small molecules and other impurities that are very weakly bound to the resin because they're not very hydrophobic. And then as you increase in this case, the methanol concentration, we see two peaks come off. And it's interesting here, we're actually running a UV 260 that's in red. I don't know if you could see the red color, and the UV 295. And so with 295 nanometer UV detection, you can see oligos, but non-oligos or molecules that don't have that UV absorption don't show up. So we can see these two peaks, but only one of them has any significant absorption at 295. So we identify that as our failure sequences. These are our shortmers. And this other peak here is a non-oligo impurity. This is most likely a benzimide that would come off in the deprotection process. And so once all that goes out, then you step it up to about 75% methanol, and boom, out comes your target oligo. And then at the end, you increase it. And we'll talk a little bit more about what some of these things are in the next slide. But this loading is on a column where we loaded just about 3 milligrams on a column. So it's pretty low loading. We wanted to show this because you could see the peaks really well. But again, people wanted to see real loadings, like what can this do? So we first had to figure out exactly what the capacity of our resins were. So we went and did just a loading capacity. So you set up a column, you just load your oligo solution, and just load and load and load until it breaks through. And that's what we do here. And these resins break through at about 50 grams per liter, 50 mg per mil on the resin. So when you're looking at the capacity of a resin to purify oligonucleotide, and this is a 20-mer antisense molecule, you can get about 50 mg per mil. And so for instance, we sell these columns. It's a 1 by 25 centimeter column, and this could purify about a gram of this because it's about 20 mil column. So about a gram of oligo could be purified in that way. So then we went and did this prep scale chromatography. And so how this goes is we just load that material right onto our resin. So this is essentially right out of the synthesis feed. It's got all the amine and got all that stuff in there. And you just load it on there. And we loaded at 80% of the dynamic binding capacity, which is about 40 mg per mil loading, resin column loading. And it was good, it didn't break through. Actually, the oligo didn't break through. You can actually see some of these impurities, the non-oligos impurities start to break through. And so once that comes off, we wash it back down to baseline, and then we do what we just did on that last slide. You just sort of stepwise elution. Off comes your DMT off material, and then your DMT on material. And actually, back in this back end, you get some like very tight binding impurities, which end up being like where you have two trityl groups on the, like a branch type materials. So very simply, you can get the DMT on from any of your short mers off in this one simple step, and a very big, good separation. So this is a material that has a diastereomer, some phosphorothioate, so it's got the diastereomer shows up as two peaks. And in one simple step here, we can take it up to very high purity. So that's for a 20 mer oligonucleotide, but we wanted to also challenge this with a totally different type of molecule. Using the same methodology, bind it with DMT on, separate your DMT on from DMT off, collect your DMT off, and off you go. So this is a 91 mer guide RNA. Again, pretty low loading, so you could see the peaks, but all your DMT, and in this way we did a linear gradient, but all your DMT off comes off very early. You have a huge space between any of your failure sequences and your DMT on target. So as opposed to, say, ion exchange, where you're trying to cut that peak of your N and N-1, this is, anything that may not have a DMT will be very far separated from your target peak. Again, let's go load this at higher loading capacity. In this case, we loaded our resin up at 17 mg per mil. Again, right out of the synthesis feed. And we loaded on. We stepped up to wash off some very weakly held impurities, and then DMT off, DMT on, and then some of those more tightly bound stuff. So we did this in our crude purity on this 91 mer was about 30% full length, and our fractions were really high. I just added some data in today if anybody really wants to see more, because we just got some of this data, that if we just take this DMT on peak and we just started taking fractions here and just looking at the purity of those by HPLC, you can see as you go through that fraction, you get some really nice high purity material as you go through there. Now, certainly there'll be a DMT off later on step, or detrilation step. In this, we did a yield versus purity analysis, so it's essentially a mock pool type analysis here, where if you look at the purity versus our recovered yield of what we put in here, you can get, we got 85% full length yield at greater than 75% purity, and so forth down the line. So that was DMT on purification with these resins. And we see that has a lot of use in really commercial scale applications. In this DMT off mode, we see this more in analytical separations, but it could be used on either. So what happens with DMT off now is now you have your oligo. It doesn't have that big greasy hydrophobic DMT group on it, so it doesn't really want to stick to a hydrophobic resins. And so you use these ion pairing agents, which have both a cationic and hydrophobic species. And so that interacts with the negative charge on your oligonucleotide to essentially make it hydrophobic, or if you want to think about it the other way, it could adsorb to the resin and make the resin now ionic. And so essentially this technique allows you to separate more by a charge difference or a length difference. So here's an example. This was a 41-mer guide RNA used in sort of a diagnostic. And we had talked about this before. There's a method here where you essentially run an isocratic to get some of these early eluting impurities out, and then run a gradient across the peak there. So you get some really good separation of your N and -1. And again, yield purity analysis of this 20 micron XT20 versus a polymeric 15 or a silica 16 micron, you can get that higher yield and purity balance from your pool. So that's a 41-mer RNA. Here goes a 25-mer DNA. Again, same methodology. I think this is probably the exact same method. It's just isocratic and then a gradient across your peak. You see these peaks on either side are at least somewhat resolved. And then your yield purity curve looks really nice compared to other types of materials. So then we wanted to challenge this, right? People always ask us, well, how can you separate N from N-1? Okay, let's do that. So we took that 25-mer that we had and we just made another one with an extra G on the end to make a 26-mer. And we saw very good resolution between the 25 and 26. And if you pull fractions, you can see where that separation all happens in there. So as part of this, we looked at some different operational parameters in terms of injection volume, flow rate, temperature. And we certainly see as you go to, as you'd expect, lower flow rates, you get a better separation. Higher temperature, you'll get a bit better separation too. All right. The last one is the pressure drop. We're often asked about, or this perception that, polymerics are more compressible than silica. And they are, but not by much, actually. And really, our polymerics are designed with this patented process that has a different structure design of the polymer that allows that bead to be more rigid than even other competitive polymerics. So as you go to higher flow rates, your pressure on your column is going to be less. Now this is a small column, but we're looking at doing some additional studies here in the future on larger column pressure drops. So what we talked about today, just to recap, if you start with an oligo coming out of synthesis and you want to get that oligo ready for whatever application you're going to, you can choose either route. And certainly you can use reverse phase resins for both of them. So we obviously have pre-packed columns and bulk resin available. We have a booth here. We have posters. Again, the poster on with some more details if you want to take a look on the high loading DMT-on purifications, as well as one on the nucleotide separations for mRNA type applications. Okay, and I'll be happy to take any questions.
Hi, my name's, oh crap. Hi, my name's Will. I work at Prime Medicine. For DMT on purification, have you found an upper limit for what length of oligonucleotide would actually just not be beneficial? Because I know as the lengths get longer, the actual oligonucleotide gets more hydrophobic, and that might not help with the hydrophobicity handle that the DMT group would give.
Yeah, well, we haven't got there yet with a 91-mer guide RNA. So I was almost expecting that as you got to bigger oligos, you'd have more trouble just getting them to fit into the pores. But we haven't seen that yet. They seem to be going in fine. We'd like to get our hands on some, 120, 140 mers and do some of these tests. So if you have material, we're happy to take it and test it and show you the data.
How you doing? Good talk.
Thank you.
Does the patented process allow for smaller bead size? Could you get below 5 micron?
Sure.
Yeah.
We could, yeah. Yeah, these are not analytical columns, right? So the technology to make the beads can cover essentially all particle sizes, but our product lines are not for analytical purposes, where a 5 micron might be more for analytical purposes. These are designed really for prep scale, large columns. You sort of take from this type size, you do your process development, and you can scale wider. I mean, these go to 60, 80, 100 centimeter type diameter columns.
Hi, I'm Lee from Turner. We're actually doing tRNA new modality, kind of 76-ish nucleotide. So very close to that 91 you showed. Very interesting. Just wonder, it seems because I heard about HIC, hydrophobic. Is there a clear line between the HIC and the reverse phase you just showed that was DMT on?
I'm not an expert at HIC, so I wish I could describe the differences there. Certainly there's differences that come with the use of the high salt. In this case, you use solvent, so there's the balance of that. You have to remove the salt at the end versus having to remove the solvent at the end. So I haven't seen where one works better than the other. I just haven't seen a side-by-side comparison, though.
Okay. Another quick question is that fair to say that DMT on is more suitable for the process than the DMT off approach is more for analytical?
With the reverse phase, we do see that. We do know of customers at larger scale using ion pair reverse phase HPLC. So it's not out of the question to be using an ion pairing agent at prep scale.
Okay. Last one. I actually checked your website before trying to acquire some resin, but it shows up the reverse phase. I guess that's the XT20 or 30. Shows critical back order. How the lead time looks like now, or if you have any clue?
Lead times are good right now. We've built up inventory, and if you have any questions about that, you can go on there. Certainly the website, for small scale orders, they're in stock, ready to ship essentially next day. For large scale orders, I mean, we could talk offline about lead times and what that means for large scale orders, but we do have inventory.
Yeah, I'm gonna stop on your booth later too.
Okay, perfect.
Thank you.
Thank you.
Hey, Francis with Ionis. So yeah, I've been using XT20, XT30 for 15 years now. For your plot with the linear velocities, I've always used the magic 153 centimeters per hour is the magical velocity we've been told the whole entire time. Is that maybe more flexible than I realized?
It's absolutely more flexible than that. These can go up to much higher linear velocities than 153. Obviously, as you get wider, you're going to lose the wall effects, and you're going to put all the pressure onto this. But I don't see that you should have any problem running at much higher flow rates than that.
Awesome. Thank you.
Thanks.
Hi, I am just wondering why you decide to use either a stepwise elution or a linear gradient.
Good question. It was sort of either or. We work with partners from this company, or from various companies, and they gave us some initial leads onto how to do that. In this case, you could see with that linear gradient, you could certainly run that as a stepwise. Some people just at lab scale like to run linear. At plant scale, I think you'd probably prefer to run a stepwise gradient. But I mean, you could drive a truck through that separation right there. And so it's very amenable to a stepwise. Typically, you'd run a linear gradient when you're really trying to pull things apart here, but it's definitely not necessary for that.
Thank you.
Thanks. All right, well, we'll be happy to answer any questions offline or at our booth later. Thank you very much.